Oui, Thias m'a demandé est-ce que ça le soit.
Et ce bière est enregistré par hasard.
Je dis non, parce qu'en plus on a eu des soucis réseau, du coup ça n'a pas fonctionné. I will also record using the system to make sure if the Zoom fails, we also have
OK.
the recording.
Oui. Ah oui. Juste with Zoom. Just with.
Oh,
So if you
I think I cannot do both.
no, but that's fine. You don't just with Zoom is okay because then you also have the camera from the laptop.
The camera is here.
Ah, okay, even better.
Okay.
Sorry.
Oh, c'est pas très bien. It should be fine. Okay. Okay, yes. Comment on fait tant?
Avec et tout.
Tu as envoyé le slide.
Oui, oui, oui.
C'est ça.
Oui, oui.
Ça m'a pris dans les animations.
Oh.
Donc tu enlèves.
Oui, parfois j'ai dupliqué un slide, c'est là. Ça, c'est ça. Ouais. Ça va. T'as pas trop dormi en fait.
So the microphone here.
Yeah.
Also recording into Zoom
Okay.
and goes to the speakers.
Okay.
So if you can just say
Yes, or
near the microphone,
like this.
or if you need to move, I can also give you a wireless microphone as you want.
Well, I like to stay a bit more on the side.
But I think I can just put it like that.
Yes.
It should be okay.
Yeah, yeah. All right. As you wish.
J'ai le plaisir de présenter Sébastien. Il est professeur à Unilever. Donc, ces travaux étaient un des premiers pour le côté intégration entre machine learning avec l'appui de métier, avec la programmation de contraintes, avec un produit, la partie pionnier qui est en qualité de 2008. Et donc, il s'intéresse toujours à l'intégration entre l'apprentissage automatique et l'optimisation sous contrainte. Et donc, comme indiqué sur sa page web, l'objectif, c'est de construire une résolution de contraintes qui tient compte des plus proches à l'utilisateur. Et donc, ça se traduit avec l'apprentissage de contraintes, l'apprentissage de préférences d'utilisateurs, l'apprentissage de l'environnement. Et il y a aussi tout le côté pour résolution de contraintes conversationnelles. Et donc, il est responsable d'un projet chatbot. On a fait le chatbot. Je lui ai dit qu'il fallait qu'il demande un brevet dessus parce qu'en fait, son projet chatbot était même avant le fameux chat qui était le plus simple. C'était depuis 2021. Et maintenant, à chaque projet, il faut demander un brevet tout de suite le nom. Voilà. Donc, je suis très ravie qu'il a accepté de venir investiguer.
Ok, merci. Merci beaucoup pour cette invitation. Et so I will do the talk in English, mais quand même, un grand merci pour l'organisation. Et le talk, so I'm definitely going to talk about topics that are close to the caviar group and theme. And so this is joint work, especially with Dimos Tsouros, a postdoc in my lab, as well as PhDs and postdocs Senna, Jay, Irfan, Maxim, and Kostis, as well as external collaborators, Fernando, James, and Victor. All right, so the title is Learning Constraints, Objectives, and Entire Models. And this is JFPC, so obviously I'm talking about constraint programming techniques, techniques that we use to solve all sorts of combinatorial optimization problems, vehicle routing, scheduling, and so forth. And so the images that you see here, just a little side note. So in our lab, we use this CPMPy library, and so they've all been solved and generated in that Python library. I'm not going to say too much about it, just want to start a bit with it. So it's very much a library like Minizinc and like PyCSP3, but what's different is that because we do a lot of work where we integrate with machine learning, and you can actually, the decision variables are NumPy arrays, so that makes integration with machine learning a bit easier. And the second point is that it's also incremental and gives you direct solver access. So when you do machine learning or when you do constraint acquisition, you need to call your solver over and over and over with only small changes to the model. And so if your library is incremental, then that can give you a bit of a performance boost. All right, so, okay. Yeah, so if we look at the way that we work in constraint programming, then in many cases we use this model plus solve approach. And CP is of course a subfield of artificial intelligence, and rightfully so. So the AI perspective to constraint programming is on the one hand the study of expressive formalism. So what kind of formalisms can we use to express problems and to express knowledge? And then on the other hand, of course, it's artificial intelligence because we look at intelligent search and propagation to find solutions efficiently and quickly. And so actually, the research field has matured a lot, thanks to actually many of you here in the room. and that's good. And so then the question is, all right, so now that techniques are maturing, what can we do more, right? If we look at the research field of AI at large, then more and more people try to incorporate more of the problem context. And so that's a bit the way that I look at this line of work as well. Namely, we're very good at modeling, we're very good at solving, but where does this model actually come from? And so most works assume that you have a problem specification, and this is true, right? This is the model, and you just need to solve it. But where does this model come from? And so if you look at it, especially a bit more in practice, then this model is typically written by an optimization expert. And that optimization expert, in turn, was in contact with multiple domain experts. I think about vehicle routing. You have the optimization expert, then the domain expert, maybe the planners, maybe the owner of the company, and then many other different stakeholders, including the drivers, including the clients, and so forth and so forth. And the problem specification leads to solutions, and those solutions impact everybody involved. And then they're all operating in a certain environment and a certain world and so forth, right? So this is how constraint programming is used in practice and the kind of impact that it has. And so this AI view to constraint modeling, to trying to broaden a bit that scope, and that's about asking that question, okay, can we actually make the entire process? And so can we not just start from the model, but can we make the entire process more intelligent? Right, so that's a bit the motivation or the view behind this line of work. Another way to look at it, a more technical bottom-up way to look at it, is that it's about the integration of indeed machine learning techniques and reasoning techniques, in this case, constraint solving techniques. And so there's lots of work in the last 10 years, let's say, that can be divided into kind of like two categories. One is where learning techniques are used as statistical, but not just statistical, to learn part of the problem specification, which is what this talk will focus about. And the other big area is where learning techniques are used to improve the solving, so to find solutions faster. So that's from a technological level. And so this is the menu for today, or at least the menu for this talk. So I will talk about three different aspects that fall in that first category. So the first one will be about learning the constraints, learning the problem specification, the structure. The second part I will talk about is about learning the objective function, the weights of the objective function more specifically. And then the third one is a bit of a look ahead, trying to, even, can we just learn everything at once? So that's the end. All right, so let's start with learning the constraints. So in the CP community, this is especially known under the name of constraint acquisition. In machine learning, it's a bit closer related at large to structure learning and also to program synthesis, which are different domains from which a lot of inspiration can be gained. All right, so learning the constraints. So the point of view here is that creating a model is not always trivial. It requires a certain expertise, that optimization expert has an expertise. And for some, it's actually a bottleneck to using the technology. And we would like CP to be used a lot within, for example, the AI research field and within the sciences in general. And so formulating that problem specification can be a bottleneck. So if we could somehow assist the user, if we could somehow help them formulate their problem, that could widen the applicability of the technology. So within constraint acquisition, I did this very nice paper by Christian on a constraint acquisition, AIJ 2017. So there's actually two big families of constraint acquisition. One is passive constraint acquisition. In this case, we assume that the user upfront, for example, from historical data, has a number of solutions of assignments that were valid for their problem at hand, perhaps also some non-solutions. And then the constraint acquisition system has to learn a problem specification that is then returned to the user. Okay, so that's passive with a data set up front. And then there's the second category of active or interactive constraint acquisition, where there is nothing given up front. Instead, the system starts a conversation and will ask questions, queries, I will give some examples, to the user who then answers. And based on that interaction, we try to recreate a problem specification. Okay, so a bit more formally, what is the input? What is the output? So as input, we typically assume that there is some vocabulary. That means that we assume that we know what the decision variables are and what their domains are. Okay, there's many ways that you can ask the user, or maybe with an interface or whatever. And typically the user does know if they're solving a scheduling problem. They do know, for example, how many nurses there are and how many skill or tasks that they have to assign, or in vehicle routing, and how many stops and how many and so forth. So this is a reasonable assumption. And then we also assume that there is this constrained language, a list of, well, not necessarily a list, but just templates of maybe even a grammar. That's the most general setting, a grammar of what kind of constraints that you can express. And so this grammar can be very expressive. That's fine. And so if you combine these two, then you can create what is typically called the bias, a large set, candidate set of constraints. And this can be huge. This can be millions of candidate constraints. And then the constraint acquisition, either passive or active, has to extract a subset, a small subset of those constraints, which is what the user will try to express. Right. So if we find this CL, this learned set that is equivalent to some unknown target set, then we succeeded. Okay, so in a nutshell, before we go more into some of the recent advancements, what is the essence of constraint acquisition? It's that there is this gigantic set of constraints, and you can think of this block as being the full list, millions of candidate constraints, and that's what you start out with. Initially, you don't know anything about the problem, so this learned set is empty, and the bias contains all of them. And then during the learning process, two things can happen, either from the data in the passive or from interaction with the user. There are some candidates that you know cannot be a constraint. And so either we can remove things from B, or as the method progresses, we can learn that a constraint certainly must be in the specification. Right? So those are the two ways in which learning happens. And this can continue and continue and continue until ideally, especially in the active case, we have converged to a set. So there's nothing in B anymore that is not actually learned. Right. So that's the essence of the algorithms, all of the methods. It's all about shrinking that list of constraints up to a point that is as close as possible to that. All right. So we will focus on interactive constraint acquisition, active constraint acquisition. And there's two types of queries that the system can ask to the user. And there's a small example here of 4x4 Sudoku. So the system itself will ask a query, will propose an unlabeled example to the user. Initially, in earlier works, this was what's called a membership query. That means that it's a complete assignment to your variables that will be shown to the user. And then the user has to answer, is this a solution of your problem? Yes or no. In case of a 4x4 Sudoku, the answer will be no. Because of this, there's other reasons as well. But the user doesn't say that. The user just says no. In case more recent works, and also the ones that we will focus on, the system can also ask partial queries, can show a partial solution to the user and ask, is this partial solution, and does this satisfy all of the constraints? And again, here the answer would be no because of that reason. But so the user just answers yes or no. And that's the basic interaction mechanism. So most active constraint acquisition algorithms follow a similar structure. Namely, the system has to generate an example, a query, a partial assignment that will be presented to the user. And so it's asked as a query. The user either, as I said, answers yes or no. If the user answers yes, then this is what we like the most. And if the user says yes, this is a solution, then anything in your bias that violates that solution, that solution will be a counterexample to anything that it violates in the bias. So anything that it violates, you can throw away. You have a counterexample. This cannot be a constraint because the user said, yes, this has to be true. So you can shrink, and from the top, you can remove violated constraint. If the user sees a partial solution and sees that this is not a valid solution, they will say no. And that's a bit more tricky. In that case, you have a list of candidate constraints that violate that example, but you don't know which of those constraints is actually a true constraint. It could be only one, it could be multiple. And so then these acquisition algorithms have to zoom in on that set of constraints to see, okay, ask more questions to narrow down that list until there's one specifically that user says, no, this partial assignment is not true, and then you can learn it, all right? So this repeats and repeats, and then under some conditions, if you cannot generate an example, then you know that you have converged, and then this method finishes. All right, so that's the basic interaction mechanism. So what are the challenges for constraint acquisition? There's two challenges, two somewhat competing challenges. One challenge is that you want to minimize the number of queries, number of interactions with the user. You would like to ask as few questions as possible and to learn as much as you can with every interaction. And to do that, you will have to be smart in which question, which query that you ask. But that, of course, requires computation time. So the other challenge is that you don't want the user to wait too long. And you want to, especially if you can imagine that this would be a real interactive session, you cannot ask them to wait 5 minutes to label another instance, right? So it also has to be fast, incrementally fast. Now there's continued progress on this problem, a nice series of papers. So matchmaker agent can be seen as a predecessor. There's the CONAC, QAC, multi-QAC, also works that handle omissions, and so forth and so forth. And I will talk about some recent works that we developed recently. Okay, so let's start by looking at this query generation process, right? So this one is really essential to reduce the number of queries, and that's also the one that takes the most computation time. So if we can find an informative query, then so the goal in generating this example is that you want to find a partial solution, right? And this partial solution should not violate anything that you already learned. If you learned it, you know it has to be true. So it would be very silly to ask something that violates what you know has to be true, right? Because then the user will say no, but you already knew it. So the partial solution, the example cannot violate anything that any of the constraints that you've already learned. But at the same time, you want to violate at least one constraint from the bias that is not in the CL. Because then if the user says yes, you can throw it away. If the user says no, you know that that's a true constraint or you have to zoom in, okay? So these two properties are an essential property of a query generation if you don't want to ask unnecessary questions. All right. Now, before 2023, almost all methods that converged correctly, they used custom solvers. Okay, so they actually had to change the way that the constraint solver works, especially the branching strategy. But if you have to change the way that the solver works, then there's this unfortunate side effect that whatever constraint acquisition algorithm that you develop, it's actually tied to that specific solver. And that also limits the applicability of the technology. I think, I wish that constraint acquisition would be usable if you use PyCSP3, if you use Minizinc, if you use CPMPy. It shouldn't actually depend on the solver or the modeling language that you use. Okay, so let's zoom in on why custom solvers are typically used. And so why typically do people change the solver, have to change the branching strategy? The first reason is that the set of biases can be huge, like millions even. And so finding a complete assignment would take a large amount of time, okay? But you don't need a complete assignment, right? In this case, a partial solution is sufficient. So as your search progresses, as soon as you satisfy this property, and that you violate at least one from B and it doesn't violate any of CL, during search, even if you haven't assigned everything yet, if you find something like that, you know that this is a potential query. So you can store it, you can continue your search, and then if the user stops the search, at least you know that you found at least one. And so this partial solution is sufficient, but the solver typically always, standard solvers don't output partial solutions, right? They just output entire assignments. Okay, so that's one reason. And then when we dug in deeper, we saw that there's another reason. There is this side case very much at the end of the acquisition process. Then what can happen is that your bias B, your set of remaining constraints, that they contain only indirectly implied constraints. All right, so what does this mean? Let's assume a simple 9x9 Sudoku with a decomposition of the all different constraints. So that means that you have 812 not equals constraints, okay? But actually, only 648 of those are necessary to find a unique solution. So even though the real problem formulation has this 800 plus constraints, 648 of them imply the remaining 162. Okay, and so when these 648 constraints have been learned, the rest can no longer be violated, right? So you cannot find a solution that violates at least one of those. But this is only an indirect implication. And so your solver will not realize this, and it will actually try to enumerate all of the possible assignments to the Sudoku. And for each of the possible assignments, it will then see, no, this is implied. None of the constraints can be violated. And then it will try another assignment, and then it will have to check that again. And so what happens is that because of these indirectly implied constraints, the solver just starts enumerating all solutions and takes ages. Okay. All right. So let's fix that. So this is a CP23 paper. And so if we want to use standard solvers, then we have to avoid this indefinite proving of indirectly implied constraints. And so when we looked at it a bit deeper, what we saw is that when this happens, typically the bias only contains a small number of constraints. In the Sudoku case, it's like 168 or what was it? And these typically do not involve all the variables. It's an indirect implication because it's an implication between the constraints that you have here and variables that are not in B, but that are in the true already learned constraints. Okay. Now, so what we can do is we can restrict the query generation. Instead of asking, here are all of the variables, find me assignment, we will restrict the variables that the query generation search over to the variables in B. Now, this is valid because a partial solution is enough. So if you only give a subset of the variables, if this is a non-empty subset, then it can compute a partial solution. So that's fine. It will return a non-empty partial solution. And right now, there can no longer be indirect implications. I know because you restricted the set of variables to only those in B. So there will be no indirect interaction between variables that are not used in B. Okay, and then this mechanism doesn't, this indefinite proving effect doesn't happen anymore. All right. So by doing this projection, one of the theoretical bottleneck is actually fixed. All right. Okay, but there's a second issue. The second issue is that what if your initial set of candidates is too large? Actually, the first query that you need to generate, let's say that this is your bias is 1 million constraints, right? If you're going to use a standard CP solver, that means that you have to reify 1 million constraints, give that to a solver, and just loading in the constraints for that solver will already take a few seconds. And so then finding a solution will take even more. So that actually would limit well, it would be a bottleneck on how long the user has to wait. And so even finding a solution that satisfies that property could take unnecessarily long. But what about cases where your grammar is very expressive and the list of constraints is even more than millions, and you can't even store all of them in a CP model if you ratify the constraints, right? So what now? Well, here we again had this idea that actually a partial solution is sufficient, and the custom solvers are such that you return a partial solution. But we don't want to change the branch of the solver. So let's just give fewer variables to the solver. If we give fewer variables to the solver and it finds an answer, then that's a partial solution, right? So that's fine. So that's where this idea of a bottom-up approach came from. Instead of using all of the variables from the very beginning, let's first take a small set of variables, maybe even 2 variables, why not? And you only ask questions. You can use any standard constraint acquisition algorithm on just a subset of the variables. Let's say 2 variables, right? You learn whatever constraint there is. After you use any existing constraint acquisition algorithm, you've actually learned of the set of constraints that have that set of variables in common, all right? If what you just learned over is a subset of your full set of variables, then you have to continue and you add, let's say, 1 additional variable to that set. So now you have 3 variables, you generate a bias, to be a small bias, right? Just over 3 variables, and you already learned everything between 2 of those. You again call any interactive constraint acquisition, and you continue like that, all right? So this bottom-up approach avoids this initial call with a huge number of solutions, okay? Because you only need to generate those for the newly added variable. All right, so that solves that second big problem, the initial this initial size. But it also creates an opportunity. And the opportunity is that now each query generation call will have relatively few constraints. So it will be fairly fast, and it will actually be so fast that finding any query is easy. So let's spend more time, let's spend more effort in finding a good solution. Okay, now that the byte is small enough, let's formulate what a good query is, and let's spend some computation time optimizing for the best possible query. All right, so okay, so before I dive into that, so now we can use CPMPy, or you can implement it on top of any solver that you like, and we will focus on generating these informative examples, and it will still converge. It's still guaranteed to converge. Okay, so we will ignore the red one for now. So this is a MQuack2 state-of-the-art algorithm. This shows the number of queries for 5 different problems. If we do this GROAC approach and with a standard solver, so where we do this bottom up, we start with 2 variables, 3, 4, 5, and we can see that actually the number of queries decreases in most cases, right? So by doing this bottom up, actually in many cases, the number of queries will decrease. And if we look at the max waiting time, then, for example, for this job shop, that's the most extreme. MQuack2, even when it uses this customized solver, the maximum waiting time is over 5 seconds. And it's in the beginning, right? It's initially when you have a large set of constraints, that's when the user has to wait the longest. So by doing this GROAC trick, that maximum waiting time decreases. Sometimes the total time goes a bit up, for example, for JSudoku, but for us, we especially focus on this maximum waiting time that the individual user has to wait. Okay, so the red one is now about selecting the queries in a bit of a smarter way. So what actually is a good query? What is an effective query? So the quality of the query, a better query, a better partial solution will lead to a faster convergence. And that means that you will have to ask less queries afterwards. And typically in prior work, people look at maximizing the number of constraints that are violated. So an example that violates as many from the bias as possible. Okay, why is that? It's not fully aligned, but why is that? There's actually two conflicting goals. Imagine that you know what the user will answer. You don't, huh? You don't know what the user will answer, but imagine that you know. if you know that the user will answer yes, then the best thing to do would be to add as many constraints as you can, and so to generate a partial solution, a partial query that violates as many constraints as you can, because if the user answers yes, you can throw all of them away. Okay. So that's when this objective, maximize number of constraints that are violated, is a good one. But if the user answers no, then you have to zoom in to find which of the constraints it is. So if you would know that the answer would be no, then it's better to violate as few as possible. If you violate just one and the user says no, you know that that's a true constraint and you can add it. Okay. So in that case, you want to violate as few of the constraints as possible. Okay, so these are clearly opposite objectives, literally. So what can we do? Well, let's imagine that we have an oracle. Let's imagine for a second that we have some kind of oracle that will tell us for every constraint whether it belongs to the true set, yes or no. Of course, if you have this, your problem is solved, right? So we won't have it. But let's imagine for a second that we know that we have this oracle and that can give an estimate. And so if this oracle says, no, this is probably a true constraint, you should aim to violate it. And if the answer is yes, this probably is a true constraint, then you should try to generate a query in which this constraint is satisfied, right? So what we will do in the paper, there's the details of this magic formula, but we somehow want to estimate the probability that a constraint is a true constraint. And then we can compare, and that's what this formula does, it compares this probability to the effect of having to do a find scope over the remaining set of variables. And the details are in the paper. But the idea is, let's try to estimate whether a constraint is true or not, and then guide the query generation based off that. All right. So this is a probability estimation problem. So let's use machine learning. Okay, so constraint acquisition is a symbolic learning approach. It's symbolic because it asks symbolic questions. But now that we identified a subpart of it as being a probability estimation problem, we can actually use statistical machine learning within the symbolic learning. All right. So the idea here is that we're not going to use machine learning to predict a solution or to predict anything like that. No, for each individual constraint, we want to predict whether that constraint is likely to belong to the constraint set, yes or no. All right. And how will we do that learning? Well, every time that we generate a query, we observe an answer from the user. And so that answer is a label, yes or no. And so we can learn from that answer to then guide the query generation. That's the high-level idea. So in a bit more detail, if you want to use machine learning, of course, you have to construct a feature representation. Okay, so every constraint we want to represent as a fixed set of features, give that to the machine learning model, and then have it estimate for every constraint whether this is in or not. Okay, so the data set will be for every constraint this feature representation, and then if it's already learned, and so if it's below the green line, the label will be true, or if it's eliminated, if it's above the red line, the label will be false. Everything in the middle, you don't have a label yet, but you do observe the labels on those two. Okay. And so that's what's written here. So when a constraint is learned, you add it to the positive instances, and when it's removed from B, you add it to the negative instances. All right. So that defines the labels. But now, what is that feature representation? So as always, the feature representation is key because it defines what kind of expressivity in a statistical way that the machine learning model has. So what we do is a first set of features are relation-based features. And so for example, they use the relation name. Is it an equals or a not equals or a bigger than, or is it a sum, or so forth and so forth. And so the relation name is one thing. The arity is also a basic property. It doesn't involve 2 variables, 3, 4, and so forth. Does it have a constant? It's not immediately clear if this is useful or not, but when you do feature engineering, you just want to throw in as many meaningful features in there, and the machine learning will decide whether it uses them or not. If it has a constant, what that constant value is, of what the sum of those constant values are. Okay. So that's everything that has to do with the relation, with the signature of the constraint. And then we also look at the variables that are involved. And here we assume that, for example, in PyCSP3 or in CPMPy, if you use a variable, and this is part of a matrix, for example, the variable itself will say that it has a certain name and it has a certain index in that matrix, in that array, in that tensor. And so we use that information about those indices. And for example, if we know that the arguments are variables that have two dimensions, then we can add a feature, for example, is the first dimension the same for each of the arguments? Okay, so for example, if you have a constraint over two constraints over all of the variables that form a row in your matrix, then that feature will actually be true. Okay. You can also take the average of the indices. You can take the distance between the indices, and you can define features over the indices of those variables. And we know that these are meaningful things because we want to learn things like on all of the constraint, on all of the rows, on all of the columns, on all of the blocks, or with a certain only subsequent elements. And this is also something that reoccurs. So the distance is 1 in that case. And so we're not deciding what exactly it is. We're just defining lots of features where the machine learning algorithm can then choose from to see what is important. Okay, an example. So the x11 is different from x12 constraint. The relation name will be not equals. Doesn't have any constants, so we fill in some meaningless value here. It's an arity of 2. These we create for each of the dimensions. So in this case, the first dimension is the same. The second one is not. Average value, the distance, and so forth. Yes. Okay. So, going back to this oracle, and so what we want is an oracle that classifies any unseen constraint as belonging to the problem yes or no. And so we can use any kind of classification technique. And so we tried that with moderate results. What worked a lot better is to use the probabilities, and because we can then define this weighted query generation for each of the constraints. We can give it a weight of how important it is to either violate it or to satisfy it. Okay, and that's what we do here. All right. So we tried a number of machine learning techniques. In the base one doesn't use any machine learning. We can also do simply counting. We just count how often the equals or the not equals constraint is used. That's a very basic counting-based probability estimation, which is a CP23 paper. This is AI 24, triple AI. We used naive Bayes, random forest, neural networks, SVM. And so what we can see is for different learning methods, some are better able to learn the relation between the different features, and so what kind of constraints are important and not. And so the best results are for random forest and for neural networks. Those are 2 columns here and here and here. If we look at the number of queries, so for this problem, actually naive Bayes is a very bad idea, and those 2 doesn't have much effect. There actually is a small difference here, but and so here actually the number of queries goes down quite a lot, here as well and here as well. Okay, so that's a very nice result. What's happening here is that the statistical machine learning is learning this preference, this probability, and that is guiding the symbolic learning to ask which question to ask, and that can actually dramatically reduce. And so up to 70% the number of queries can be decreased compared to no guiding, and up to 56% compared to not, to simple counting based. These are large numbers, right? In that timeline, it hasn't happened a lot that the number of queries in the best case is reduced by that amount. So there's an additional decrease if we do it not just in query generation, but also in the other elements. Okay. And so the maximum waiting time is up to 2 seconds. So even though we're evaluating a machine learning model and we're solving a weighted max CSP problem. Even so, because of this GROAC, it's only up to 2 seconds, which we think is acceptable. Okay. So yeah, so that's the no. So here the effect is more visual and the no guiding. All right, good. Some of the open challenges. Oof. Looks like my menu was an overestimation. Okay. Open challenges, number of queries. It's still quite large. So can we reduce the number of queries even further? I think one very promising avenue is to use more expressive types of queries to have more expressive interaction with user, not just having them answer yes or no, but also getting different kind of feedback and being able to generalize the individual constraints. And because typically we write like for all rows, this constraint and so forth. And so being able to generalize in that way would be very nice here as well. Also, a lot of works now focus on the constraints with small arity, 2, 3, 4. I think there's a lot of interest in expanding this work to also better contain global constraints or linear inequalities with lots of parameters. Very much an open challenge, interesting open challenge as well. And also many techniques now assume that the user is always correct. So that when they answer yes, it's yes, and when they answer no, it's no. But if you can assume noise in your, if the user might not be as attentive as you wanted, then actually your algorithm will collapse. And so being able to support noisy answers is also a very interesting open challenge. And I think here the use of machine learning will be more important as well. Okay, so the code is available at this location. You can just download it. You can use any solver that's available in CPMPy for all of these instances. Okay, our menu. What's my timing? Like until when? Okay, let's do this. All right. This was the biggest part of the talk anyway. But I do want to highlight also a very interesting recent work on learning the objective function. Not even the structure of the objective function, but just the weights. Okay. So this again comes from revisiting this model plus solve paradigm. In many cases, the weights in the objective function or even the weights in the constraints, they're assumed to be given as data. But are they really facts? Are they really true? No, in many cases, they're actually estimations. And for example, you want to minimize the expected energy cost. So that means that the weights in your objective function are estimated predicted electricity prices or predicted travel times or predicted demand or duration and so forth and so forth. Okay. So what's happening in that case is that these are predict plus optimize problems. First, there is some set of data. For example, for energy prices, we don't know what on the day ahead market, what the energy prices for every hour of the coming day will be, but we do know what the prices of the days before were, and for example, what the weather will be, what the wind forecast is, and so forth. So we can use machine learning to then get estimated prices, estimated demand, and so forth, and then solve it. And so the question here is, we're actually using machine learning for some downstream optimization task. Okay, so if we do the machine learning independently, that's possible. But if we know that we're doing the learning for some downstream task, let's evaluate what the error of the prediction is, not just here at the data level, but after solving. Okay, and if we can evaluate by solving, then maybe we should also not use a loss function, a standard mean square error loss function, but maybe we should use a loss function that takes the effect after solving into account. Okay, so that's this idea of decision-focused learning. And so again, we want to predict, for example, the hourly energy prices, and then solve some energy-aware scheduling. And so it's the same figure again. And so it could also be about predicting steel defects to optimize waste production, predicting the value of coins at clients or the volume of trash at clients, and then doing some routing problem over that and so forth. Okay. So there is potential to integrate the solving into the learning. This is one of the worst results that we got. So this shows training, number of epochs over training. So what we can see, the green line is the mean square error, a traditional regression measure in machine learning. And as the learning gets better and better and better, if we would actually solve the decision problem, the optimization problem, and we would look at the regret at how the errors impact the solution that we compute, then even though the machine learning method thinks it's getting better, in terms of the optimization problem, it's getting worse and worse and worse. And so that means that traditional machine learning metrics like mean square error, which average the individual errors, are not, in some cases, especially if there's a lot of noise, are actually not appropriate. And that's because our solver does joint inference. So it takes each of the 24 predictions at once and then computes a solution. And so some of the errors will be worse than the others. I have a small example here. And so why is using regret as a loss function so difficult? So let's say that we have an abstract problem with two items. Okay? And this is the true value that you should predict. So value item 1 should get value 2.5, and item 2 should get value 3, meaning that you're going to choose item 3. Right? If your prediction is correct, the value of item 2 is higher than the value of item 1, and so you're going to choose it. Okay. Now let's say that you're doing training, and at every iteration the weights change a bit. So if you would overestimate in this direction, then for all of these, they would clearly have a bad mean square error. The predictions would be, but the optimal solution doesn't change. For any of these points, you're still going to predict the outcome of using a prediction is that item 1 is chosen. But if you would change your prediction a bit and you would jump to this prediction, for example, then the outcome of calling the solver will change. As soon as you cross this line, you will then, the solver will then choose item 1 instead of item 2. Okay, so if you would plot the loss function or the gradient that you get for a changing weight parameter, at any point you can change the weights, but the solution doesn't change until you're in this critical point, and then a tiny change in the prediction will make the solution jump to another solution. Okay, and so this is non-differentiable. You cannot use gradient descent learning in neural networks and so forth. Right? Yes, the animation here is a bit lost. So I wanted to show you that if we would have a loss function, then the change required to gradient descent is very small. It's actually very easy to implement as long as you can define some kind of loss function that you call the solver, and then you define some kind of loss function that you can get a gradient from. And so the real tricky part is this part, getting a gradient over your constraint solver. And so I just wanted to highlight that we just have a survey that is about to come out in JARE, Journal of Artificial Research. It's called Decision-Focused Learning, Foundation, State-of-the-Art, Benchmarking, and Opportunities. And so there we discuss in detail techniques that assume a primal dual solver, like an LP solver, or even an integer linear programming. So that's 2 families of techniques. And then we also talk about 2 other families of techniques that place no assumption on the solver. So you can use any CP solver here, for example, by perturbation or by surrogate loss functions. And then you can do this kind of end-to-end learning where you call the solver in every epoch for every solution, for every instance. The paper also contains benchmarks and implementations, different solvers, different assumptions on the decision variables, on the predictive model, and so forth. Right. So I just wanted to highlight that this is also a topic on which there's been major advancements, especially in the last 5 years. Okay, back to the menu. So far, so good. Eh? So we talked a lot about learning the constraints, the structure, symbolic learning now with some machine learning to guide it. We talked a little bit about learning the objective, but what about learning the entire model? As since November 2022, we're in a new age. I do believe so, because of large language models, especially the impact that ChatGPT has, where large language models are used as a coding assistant. Okay, people, even I sometimes nowadays use it and ask it, oh, how can I best implement this or that? Or here's some code, how can I make it faster, and so forth. So using large language models for coding tasks is a thing. So can we also use it to solve or to model constraint programming problems? Right? That's the final question I want to touch. This is a paper that just was accepted. Well, this is not a paper, but it just got accepted at CP last week. So in the large language model world, this is very old because of the pace at which no, it's a joke. Like it goes so fast in the large language model world. Okay. 1 week, sometimes some people find it old. No, it's a joke. Anyway, so the idea is that you start from a natural language description of the problem. All right. So we assume that the user speaks or types in a description of the problem. For example, your client has 60,000 available to invest, and the money can be placed in this or in that. And okay, so a natural language description of the problem. And so at EMNLP 22, so before ChatGPT, there was this competition, NL for Opt. A first data set where natural language descriptions of simple linear programmings were formulated. And then the challenge was to do named entity recognition, so to discover what the variables and the constraints are, or to formulate an entire model. Okay, so we then build on this, and we actually looked at because this was pre-ChatGPT, a lot of the techniques they fine-tune BERT, like the previous generation of natural language processing techniques. And so we looked at in-context learning of large language models like ChatGPT and so forth and so forth. Okay, so we got 2 data sets from different papers. So this NL for Opt data set, logic grid puzzles, and then my colleague Gerda, she also has exercise sessions that she teaches. And so we also added some questions from those exercise sessions to see if large language models can assist in solving that. Okay, so I really shouldn't talk about it. So the naive thing is to ask a large language model directly for a solution. This is crap. That's what we all expect. I can confirm this is crap. Even if you do a lot of prompt engineering step by step and the student was really diligent, it's still crap. So one thing is that you can ask the large language model, here's a specification of the problem. Here are some examples in context of a specification and a constraint specification. Now model the new problem as for example, in our case, CPMPI model, and then let's give it to the solver and find a solution. And we added some additional steps. And so this is an example of such a problem specification, and this is what it should output. And then we had this idea of what we teach our students is to think in terms of decision variables, constraints, and objectives. So let's prompt the large language model. Let's force it to also first rewrite the problem, disambiguate it a bit into decision variables, constraints, and objective, and then ask it to produce that. Okay. So I cannot go over the details. Evaluation is very tricky, and I think the main point to address when going further and using large language models, how to evaluate that what it outputs is correct. Lots of challenges I cannot talk about. So as I said, this is the NL for Opt. If you directly ask for a solution, 11%, that's still quite a lot, I think. 11% are answered correctly, the solution is correct. If you directly output a CP model, 81%. If you do this blueprint model and some extra, it increases still a bit. For these logic grid puzzles, like the zebra, or the Einstein puzzle, then blueprint model also helps, but some additional tricks do not. Things I cannot discuss. Just one thing I wanted to highlight. So these are data sets. There's like hundreds of examples on each of these categories. So let's look now at what we give to our students in a course. All right, this is the first exercise session. So easy problems. LLMs are able to solve this. I think there's 5, right? So 3 out of 5, I guess, 4 out of 5. At the first exercise session can still solve a lot. The second exercise session is harder. Can solve fewer. The third, even fewer, and even fewer. And so this shows that there's still a long way to go for the kind of problems that we ask our students to solve, and having large language models correctly specify the constraint specification. Lots more to do. Okay, this was the menu. Yes, I should really stop. So the ERC project, it's about learning from the user. It's about explaining techniques. It's about stateful interactions. And I'm hiring postdocs should you be interested. Okay, thank you very much.
Your model can improve from the you ask for query where you consider model competence association, but here you are considering partial association. But maybe the user cannot enter this partial association because the problem is the NPR for NPR. And you can have something like, I don't know.
So if it's NP, it should still be easy to evaluate a solution, right? That's the
for the solution, but not for a partial solution. Even if you have some constraints, maybe the user is not aware of the constraint of the problem.
yes.
To do is okay, quite easy.
Yeah.
Like,
Yes. So there is work in this. We assume that the user always answers something and that it is correct. There's two things. One is a work by Demos from earlier is with omissions, so that the user can answer I don't know, and then another query is generated, and so nothing is done. I think the main thing, so you can only learn what's in your grammar that generated the bias. So if there is some constraint that is not in that grammar, then this method will not be able to learn it, but it will be able to learn all of the other constraints. But yeah, omissions and as well as noisy answers are an important challenge.
and it's really dependent of the language. Let's consider, okay, I'm learning CNF, 3 CNF. And okay, I know the variable, but I cannot learn any function with 3 CNF. Okay, except if I add variable. And it's possible to say, okay, I can add variable in my.
So yeah, well, but those are two things. So if it's a 3 CNF, you can learn it, but it's true that if there are auxiliary variables,
Maybe you need it for express also function.
yes. So auxiliary variables are not part of these standard constraint conversion techniques. I think one thing in which we overcome it sometimes in the passive learning techniques is if your grammar allows richer expressions. And so why do we typically use auxiliary variables? It's because it's some decomposition of an equality, for example, or of a nested function. And so if your grammar can stay at that form, you don't need to have auxiliary variables. But that's like only one possible approach, because indeed they assume that all the variables are given, including the auxiliary ones. Yes.
Okay, maybe I have a last question. Small question. Yeah, maybe we can also use some notification, because okay, some high-level language. Because here it's because when I consider only applicant or solution is quite poor. Maybe I can ask something like, okay, is for all X
Yes, I absolutely agree. So richer queries. So for example, asking, instead of just showing partial, asking, is this a true constraint, right? Yeah, that's very much a very interesting avenue. Yeah, or even generalizing, like, if this is a constraint, maybe this expression is as well. Yes, very much. Yeah.
Yes, I have a question on the last part that we went very fast.
Yes.
Thing I didn't get it. The conjecture is that it will be easier for the LLM to generate in this format than directly to generate mini-named code or
of the blueprint model. Yeah. So in large language model research, there's a lot of work on prompting, on actually asking the large language model to reformulate something. And so why is this tricky? One reason is that there might be ambiguities in the problem specification. And the second part is that you need to go and satisfy the syntax of minizinc, or in this case, CPMPI. So these are two different challenges. And so our hypothesis was, let's split it. Let's first ask it to reformulate it in terms of variables, constraints, and objectives. And then it can, well, focus is not the right word, but then it's especially about the disambiguation. And then the second step is, let's then give it this, and then ask for something that is syntactically correct. That was the idea behind it. It helps a bit on those data sets, but it doesn't help on the problems that we give to the students, to our surprise. Yeah.
Well, I have questions, but I will put at the right time.
Okay.
Respect.
Yes.
Is on the how to detect when there is noise. The wrong question, the wrong answer. When one is answer with the wrong answer, it will be maybe a learning problem.
Yes.
But the practice that you might have not much of data.
Yes.
Kind of data you will collect.
Yes. Yes, so if the user can answer wrong questions, I think that the statistical learning will become even more important, but the number of queries will also increase for sure. But you can just keep asking, right? So, yeah.
Thank you very much.
All right. You're welcome. Thanks.